There's something about black holes that excites our imagination. Maybe it's the fact that for a black hole to exist, a star must die. Or maybe it's the fact that whatever goes into one cannot escape. Or the idea that in the heart of a black hole, time and space don't work how we expect them to. Whatever the answer is, black holes, and especially what lies in their center, the so-called singularity, are the most enigmatic phenomena in the universe. For over 100 years, we've been living in the universe defined by Albert Einstein. His theory of general relativity made it possible to explain everything, from the origin of the universe to the orbits of the planets. His theory was revolutionary, but Einstein never imagined the astronomical phenomena we now know as black holes. These are regions in space where gravity is so powerful that nothing, not even light, can escape once it enters. And even though the first image of a black hole would only be taken in 2019, the proof of its existence was already there, in Einstein's equations. But he refused to accept it because he didn't think that such a thing could exist. Accepting the existence of black holes would have meant recognizing that at its center lies the singularity, where all the laws of nature as we know them stop working. Einstein's decisive rejection of black holes, which he published in the most respected mathematics journal in the world, created an obstacle to their investigation. After all, the father of general relativity was saying that they were impossible. But in 1965, physicist Roger Penrose managed to demonstrate mathematically that in Einstein's universe, singularities are not only possible, but inevitable. It was because of his findings that Penrose was awarded a Nobel Physics Prize in 2020 at 89 years old. However, the complete acceptance of black holes by the scientific community doesn't mean that all its mysteries were solved, much less the ones related to singularity. These concepts are very complex, so I'll start explaining the formation of black holes using something more common. This wooden table. You can see a table and feel that it's solid, but its density is just a few grams by cubic centimeter. And the scale of black holes, this material is too light. To turn this table into a black hole, we would have to compress it until its density became incredibly high. The problem is that this material will resist compression. And the more I try to squeeze it, the more I put pressure on it, the bigger its resistance will be. We would need a very powerful event in order to generate enough energy around the table to compress it to a volume so small and so dense that it creates a black hole. One type of event capable of liberating such an amount of energy is a supernova. That's what happens when a massive star, meaning a star that is at least 30 times larger than our sun, dies, and in a matter of seconds explodes. After that, it collapses in on itself, forming a black hole. This process is responsible for the formation of stellar black holes, which are the most common ones. According to the most recent calculations, there are between 10 million and a billion of them in the Milky Way alone. There is also another type of black hole called supermassive, which astronomers believe lie in the center of almost all the major galaxies, including ours. In fact, Penrose didn't win the Nobel Prize alone. He shared it with Andrea Ghez and Reinhard Genzel, who discovered an object in the center of our galaxy believed to be one of these supermassive black holes. I say believed to be because what they know is that in this region there is an invisible object which is so heavy that it causes all the stars around it to move at impressive speeds. To understand why this could be a black hole, we have to think about the celestial bodies with mass and imagine space, which is technically called space-time, as an elastic bed. But let's take it slow. The Earth and the Moon are examples of celestial bodies with mass. The first one, of course, has more mass than the second. Earth's mass distorts the space-time around it, but it also distorts the one around the Moon. This is the reason why the Moon orbits the Earth. But the star that forms a black hole can be from dozens to billions of times larger than our sun. Like we saw in the wooden table example, after it collapses, the star's mass will be compressed to a volume infinitely small and dense. Because of that, The distortion it will cause around it is so powerful that nothing will be able to escape its influence if it comes close enough. This point of no return is called the event horizon, a kind of boundary around a black hole that separates what's inside it from what's outside it. When something crosses this limit, it cannot go back. It gets disconnected from the universe, and we don't know what its final destination is. What we do know is that once inside, everything moves toward the singularity, the center of the black hole. And it's there that space and time, as we know them, cease to exist. This is because, at that point, Einstein's equations don't work. In fact, none of the laws of physics that we know so far work. That is why some say that black holes, and more specifically singularity, are the biggest unsolved problem in theoretical physics. It is where scientists have to admit that our knowledge of the universe has a limit.